Section 1.4, comparing graphs of linear motion. We're going to continue studying graphs that depict the motion of objects moving in a straight line. We've studied position time graphs, velocity time graphs, and today we study the final type of graph, and it's an acceleration time graph. Now there's only one shape that an acceleration time graph can look like in this course, because the only type of acceleration that we look at, if an object's accelerating, its acceleration will be continuous. So all acceleration time graphs will look like a horizontal straight line. And we can actually determine the acceleration of the object just by reading off of this graph. So I know that the acceleration of this object is 4 meters per second squared west. So there's more information than just reading off an acceleration time graph. Another thing we can do is find the area under an acceleration time graph. And the area under an acceleration time graph represents the change in velocity of the object. And keep in mind, it's not the velocity of the object. I've underlined this because it's the change in velocity of the object. So in our first example, we want to determine the final velocity of the cheetah after 5 seconds. So what essentially we want to do is find the area under the curve from 0 to 5 seconds. Since the shape that is shaded in under this curve is a rectangle, we can find the area by finding its base times its height. So the base of this is 5 seconds, and the height is 4.0 meters per second squared west. If we punch this into our calculators, we get 2.0 times 10 to the power of 1 meters per second west. And we notice that the units reduce to meters per second. And meters per second is the unit for velocity. So we've found a velocity quantity here, and it's 20 meters per second west. The question asks, what is the final velocity of the cheetah? But what we've determined, the area, is the change in velocity, delta V. So if the cheetah started from rest and its velocity changed by 20 meters per second, then its final velocity would be 20 meters per second. What if the cheetah didn't start from rest? What if the cheetah started at a velocity of 5 meters per second west? What we've determined is by how much its velocity has changed during the 5 seconds. And we determined that it changed by 20. So if it started at 5 and its velocity changed by 20, then its final velocity would be 25. So remember that when you find the area on a curve, you're not finding the final velocity, but rather you're finding the change in velocity of the object. So here's a summary of the 3 types of graphs that we studied: position time graphs, velocity time graphs, and acceleration time graphs. And each of these graphs are depicting the same type of motion, uniform acceleration. So this is what a position time graph would look like for uniform acceleration, what the corresponding velocity time graph would look like for uniform acceleration, and what the acceleration time graph would look like for uniform acceleration. Now, when we take the slope of a position time graph, that gives us the velocity of an object. So when we want to go from position data to velocity data, we use a graph and we find the slope. So right here on this arrow, we will write slope, because that's how we go from position information to velocity. If we take the slope of a velocity time graph, that information gives us the acceleration. So when we want to go from velocity information to acceleration, we take the slope of a velocity time graph. Now, taking the slope is not the only skill that we have studied. We've also been able to take the area under a curve. If we take the area under an acceleration time graph, that'll take us from acceleration data back to velocity data. Similarly, we can take the area under a velocity time graph, and that'll bring us from velocity information back to position. So taking the area under a velocity time graph gives us the displacement of an object. This chart summarizes the skills that we've collected when dealing with graphs of motion. If you want to determine the position from a position time graph, you simply read it from the y-axis. If you want to determine velocity from a position time graph, you would have to take the slope of the position time graph. If you want to take velocity information from a velocity time graph, read it off of the y-axis. If you need to get velocity information from an acceleration time graph, you're going to need to take the area under an acceleration time graph. If you want acceleration from a velocity time graph, you need to take the slope of the velocity time graph. And finally, acceleration is read off of an acceleration time graph. We're going to show you how to generate position time and acceleration time data from the following velocity time graph. So this is a velocity time graph depicting uniform acceleration. In order to gather any information about position or displacement, we're going to have to take the area underneath the curve. And we're going to do this by each interval of time. So the first interval of time that I want to look at is this interval right here. And I need to determine the area of this shape underneath the curve. Now this is not a regular shape. It's not a triangle or a rectangle. It's a trapezoid, but we can break it up into a triangle and a rectangle to make our area calculations easier. And that's what we're going to do first. We're going to determine the displacement and therefore resulting position of the object after the first 0.5 seconds. And then we're going to plot this data on our new position time graph. So to start, the object started at 0. At 0, there's no area under the curve, so the object has no displacement and is a position of 0 meters north from the start. In order to find out the area under the curve for the first interval of time, the area is equal to A1 plus, this should read, A2. A1 is a triangle, base height over 2. And A2 is a rectangle, base height. So let's do the triangle first. The base of this triangle is from 0 to 0.5, so the base is 0.5 seconds. And the height of this triangle, it's going from 2 meters per second north to 3 meters per second north, or 3.5 meters per second north. So it's 1.5 meters per second north. And we're going to divide this by 2. Now the rectangle has a base again of 0.50 seconds. And a height, this rectangle goes up to 2.0 meters per second north. If we simplify this, if we add up the area of the triangle and the area of the rectangle, we end up with 1.4 meters north. And if we were starting from 0, then our final position after traveling this 1.4 meters north is 1.4 meters north from the start. So what we've done is determine the displacement over the first interval of time and our resulting position for our first interval of time. So let's determine the displacement covered over the second interval of time, and we're going to find the area of this segment on the graph. And because it's in a regular shape, we'll break it up into two more common shapes. We'll call it B1 and B2. Take a look at triangle A1 and triangle B1. You notice that they are identical. So they'll have the same base and they'll have the same height. The only thing that's changing in this example is the height of the rectangle, B2. And in fact, in all of these examples that we do, the little triangle segment will be the same for all of them. So let's determine the displacement during this interval of time. And the displacement is found by finding the area of B1 plus B2, which is the triangle BH over 2 and the rectangle BH. So I told you that the dimensions of this little triangle are the same as that for A1. So that's 0.5 seconds high times 1.5 meters per second north divided by 2. And the rectangle has the same base, 0.50 seconds, but its height is different. So this rectangle goes from 0 all the way up to 3.5. If we simplify this, we end up with a displacement over this time interval of 2.1 meters north. Now, if we continue to travel in a straight line, we started off at 0, we traveled 1.4 meters, now we've traveled an additional 2.1 meters. So our position from the starting point is 2.1 plus 1.4, which is 3.5 meters north from our start. Let's find the displacement and resulting position of this third interval of time. Call it C1, C2. And we can determine the displacement by finding the area of triangle C1 and rectangle C2. Triangle C1 is the same dimensions as the previous ones, so 0.50 seconds times a height of 1.5 meters per second divided by 2. And the rectangle has a height of 5.0 meters per second north. So if we add these up, we end up with a displacement of 2.9 meters north. So we've traveled an additional 2.9 meters north. So if we were at a position of 3.5 meters north and traveled an additional 2.9 meters north, our final position after this interval of time is 6.4 meters north from our start. We have a final interval from which to determine the displacement. I'm going to label it D1 and D2. So let's find the area under this segment of the graph, thus finding the displacement under this segment of the graph. Triangle D1 is going to have the same dimensions as all the rest, 5 seconds times a height of 1.5 meters north over 2 plus the rectangle base is the same, 0.50 seconds, and the height of this rectangle is 6.5 meters per second north. If we simplify this, we end up with 3.6 meters north. And if we've traveled an additional 3.6 meters north, we end up with a final position of 10.0 meters north from the start. So now that we've finished collecting position information from this velocity time graph, we're going to plot the time versus the position. So I've set up a graph. I've used the same intervals of time as above, and I'm going to label the y-axis so that it covers a span of 0 meters to 10 meters. So I'm going to go up by 2s. And on this graph, I'm going to plot all of the values that we've determined. So the first was a position of 0, 0. The second, at 0.50 seconds, we covered a distance of 1.4 meters per second. After 1 second, we're at a distance of 3.5. After 1.5 seconds, we're at a position of 6.4. And after 2 seconds, we're at a position of 10. If we join these points with a smooth curve, you see that we get an upward curving line. And we could have predicted this. This is the shape of a position time graph that's depicting uniform acceleration. So it takes a bit of work to go from a velocity time graph to produce the corresponding position time graph. What about if we went from a velocity time graph to an acceleration time graph? This is a lot easier. So in order to determine the acceleration from a velocity time graph, all we have to do is find the slope of the velocity time graph. So we're going to use the velocity time graph from the example above, and we're going to find the slope. And slope is equal to v2 minus v1 over delta t. So let's take a look at the graph above. If we choose these 2 points, we have 8 meters per second north, 2 meters per second north at t equals 0 and t equals 2.0. So let's sub in the values. (8.0) minus 2.0 divided by 2.00, we end up with an acceleration of 3.0 meters per second squared north. So what will this graph look like? Well, at each of the intervals of time, the acceleration is going to be the same. So if we label this axis, at each of the intervals of time, the acceleration is uniform. It's 3 meters per second squared north. So our corresponding acceleration time graph is going to be a horizontal line with no slope, whose y-intercept is the value of the acceleration, 3.0 meters per second squared